Hello, Pre-Algebra, and welcome to lesson 9.1. This is about functions. Now, we actually already, functions may give us a little bit of a scare, but we actually already know everything that we really need to understand functions and to operate with functions. So let's go ahead and take a look at what functions are, and hopefully you'll see that this is nothing really new. This is just stuff that we've seen before, but now in a slightly different light. So here we go. Let's start with some definitions here. A function is a relation in which each element of the domain is paired with exactly one element of the range. And this is actually where we're going to pause for a moment. This is the key part of what we mean by a function. The other things here about the independent and dependent variables are important. We're going to be using them later. But right now, to just simply identify a function, this is what we need to know right here. One element of the range per domain. So let's finish reading the definition, and we're going to apply this definition to our function and not a function tables over here. The domain contains all values of the independent variable. So this means that this is an independent. These are the independent variables. D-E-N-T variables. Okay. These values are chosen and do not depend on the other variable. Okay, so that's an important thing. We're going to see that actually here in just a little bit, but that's important. These are chosen values and they do not depend on the other variable. Okay, now our other variable is the dependent variable, which happens to be range. This is also a dependent variable, which means that its value depends on the value in the domain. Okay, so it is tied to the domain. Now the other thing to remember here is that the domain is also X and range is Y. Okay, so we need to remember that. When we're talking about sets, remember, like if we're going to plot on a graph, right, we could write this first function here as 2, 1, domain, or X, Y, and then our next one, 4, 3, that's X and Y again, right, and you get the idea. 5, 4, and 9, 7. Okay, so we need to remember that. Now over here, this is not a function because in our domain has 2 of the same number, or we might say that 2 is connected to 2 numbers in the range, which is not possible. Or at least this doesn't make it a function. It can't be a function if the 2, right, if we were to cross that 2 out, we could also say that 2 is tied to 2 numbers in the range, which means that it is not a function. Okay, so let's take a look at what that means with a couple examples. So let's determine whether each relation is a function. Explain. So here's our first relation. And here, we're not going to worry about y. Remember, we said that this is y, this is the dependent. So the second number in each set, or in each set in the relation is a y. So we're not worried about that. If that repeats, that's okay. What we are worried about is the x, the first number here. And that is what we want to worry about. So as soon as we see it repeating, we know it's not a function. So let's take a look. 54, 56, 55, 54, oops. There's a 54, and there's a 54. So already this is not a function. Let's continue though. After 54 is 56 again. So, two reasons. Not a function, right? 54 and 56 repeat. Right? This is domain, right? These are domain numbers or values. Okay. Let's check down here. So again, in this case, our numbers are given to us a little bit differently, but we're going to use the same principle to determine this. We're not going to worry about the y to determine if it's a function. We're just worried about our x. 4, 7, so 4, 7, 6, 3, 5, 2. No repeats. This means this is a function. Okay? All right, are we good with that? Again, that's because each domain value is paired with one range value, right? So each of these is paired. There isn't two 4s, there isn't two 7s or something like that in our x range. All right, let's continue on. We can also determine whether a relation is a function by applying the vertical line test to the graph of the relation. If for each value of x in the domain, a vertical line passes through no more than one point on the graph, then the graph represents a function. If the line passes through more than one point on the graph, it is not a function. And so oftentimes we will use something like a ruler, the edge of a piece of paper, your pen or pencil, right, to look to see if at any point going along the x-axis only, we're only worried about a vertical line, right? So we are going perpendicular to the x-axis. This is the line we're drawing here, we're making, not this line here. Okay, we are worried about this vertical line. So if we can draw, if our line passes through 2 points on the graph, or on the line that's drawn on the relation that's drawn on the graph, as it's going to do here, actually at any point, but in particular where the points are purple. Let me change this color so you can see that better to green. Right here, purple is going to pass through value 4. So we're going to have 4, 2, that's this one here. Ooh, let's try a different color. That green is losing up. Yeah, here we go. Right, so this point here is 4, 2, and this point here is 4, negative 2. And since our x, we have 2 4s in our relation in x, we know this is not a function. All right, so let's take another look at this. Over here, right here, they have drawn a vertical line crossing through the x-axis on our graph. Right, so here, there's only one point where it crosses. That happens to be here, so we're good. We can have some really funny right lines. They don't have to be straight lines. Here we have kind of a U shape, and we'll talk about what that is later, right? But again, it doesn't matter actually anywhere where we draw our line. It's only going to pass through this U shape on our graph at one point. At this particular line, it's passing through it right here. Right here we have kind of a wavy line. But again, no matter where we draw that vertical line, if I can draw a vertical line, it's only going to pass through that point at one place, which means that there is only one, right, that the x value only has one matching pair. Same thing, another funny looking line here, but the same idea. Over here, notice, right, that our vertical line is going to pass through the relation twice, right? When we have kind of this C shape, right, that vertical line passes through the line here at a positive y value of 2, and here at a negative y value of 2, but at both places we're at 5 on our x-axis. So we have two 5s. Here at the circle, we're always going to pass through the line twice. No matter where we draw this vertical line, we're going to pass through it. Well, here we wouldn't, but again, our test is anywhere on the graph. If it passes twice through, if our vertical line passes through the graph or the relation twice at any point along that line, it's not going to work, right? So again, here, not a function, because at this particular point we have 1, 2, 3 points that it's passing through, all at -3, x value of -3. Notice if we were to draw the line here, and we were only to look at it here, we might say, oh, that's a function. But we have to do that vertical line, right, start at one place, and then just kind of drag it across to see if at any point that happens. Same here. If we were to draw it here, there would be one point. We might be tempted to say it's a function, but it's not a function, because as we continue to draw our lines and check, we can see that there's at least one, in fact there's several places where our vertical line passes through the graph in this kind of sideways V multiple times, which means that we have at this dot a value of 3, 2, and at this dot a value of, or a relation of 3, -2, right? X, 3 is repeating itself in the X domain, not a function. All right, let's look at this last one. Now this one, we have to remember, in this one, we have to remember what this open circle means and what this closed circle means. Remember, a closed circle means either greater than or equal to, or less than and equal to. The important part is equal to. The open one means simply greater than or less than. So that means that here, let me erase these again. That means that this dot here is -2, right? It includes -2. But this one here, the open one, is anything up to but not including -2. So in this case, since the line starts at -6, right, this -2 is going to be, that dot means that we only get to -2.01, for instance. It's not actually -2. It's going to end right before -2. So if that means that it's -2.01 and the green one that I circled is -2, those are technically not the same. Okay? And so we could write this as, right, the 2, 1, going back to green, is -2.1, and the orange one as -2.01, 0. Which means that it is still a function because the x is not the same. Now, if this one here was filled in, if this -2 here was filled in and they were both solid red dots, or if the green one that I circled was actually an open circle, then it would be the exact same value and it would not be a function. But we see that those overlap, and then we see that here we have an overlapping one as well. But again, it's an open circle and a closed circle. So this is a function. Okay. All right, let's continue. We can use functions to help us with some real-world problems. So a function rule describes the operation or operations performed on the domain value, the input, to get the range value, which is going to be the output, and can be used to write an equation that relates the variables. A function that is written as an equation can also be written in a form called function notation. So if we consider the equation y equals 2x plus 3, which I have provided for us here, that's the equation, we can write it in function notation as fx equals 2x plus 3. Okay, and what we've done here is we have said the function of x equals 2x plus 3. And that's because of that relationship there, right? The function of y, or y is the function of fx. So the variable y and fx both represent the dependent variable here. In other words, y. In the example above, when x equals 4, fx equals 11. Why? Well, because if fx equals, or if x equals 4, right, then we have f times 4 equals, actually we don't even need to do it this way, but 2 times 4 plus 3. So f times 4 equals 8 plus 3, so fx equals 11. Or, yeah, sorry, just messing with my pen there. Okay, so let's try this on a couple. If fx equals 4x minus 7, find each function value. So if it's f5, we're going to rewrite this as, so our equation is now going to be f times 5 equals 4 times 5 minus 7, which is going to be 4 times 5 is 20 minus 7. So that is now going to be f times 5 equals 20 minus 7, which is now going to be f times 5 equals 13. Okay. So the function of 5 is 13. Down here, the function of -6. Notice what we're doing here is we're taking that 5 and making that 5 the x. So that 5 went here and it went here. Now with this one, -6, we're going to do the same thing. We're going to substitute -6 here and here for x. So f times -6, or the function of -6 equals 4 times -6 minus 7. 4 times -6, right, is going to be -24 minus 7. We add those together and we get -31. Okay, so again, the key thing is we're just substituting, where we're told the function of a actual value, we're just substituting that into our equation to find the function value. All right, we may also be asked to use this to set up or to solve write a word or verbal problem. So let's see how this might work out. Mariah spent $22.50 downloading songs to her digital music player from an online music store for 90 cents each. The first thing this question is asking us to do is to identify the independent and dependent variables, then write a function to represent the total cost of any number of songs. So, what is the independent and what is the dependent variable? Okay, well, we know how, right? If we think back to some of our other word problems, we know how we're going to get $22.50. We're going to times the number of songs she downloaded by 90. So which is dependent and which is independent? Well, since the total cost depends on the number of songs purchased, the total cost, or C, is the dependent variable, and the number of songs purchased is the independent variable, right? That's because total cost, in other words, the $22.50 is dependent on how many songs she downloaded. Okay, so this is dependent, or we might think of it as the Y, right? And 0.90 is the independent. That value, it doesn't matter. That value stays the same regardless of how many songs she downloaded. So we could write a function then as cost times songs equals 0.9 times songs. Right, and this is our total cost. We know that C times S is $22.50. So if we write any function here, we know, right, that C times S equals 0.9 times S. We know that CS as our dependent variable, it was given to us, this is total cost, that's 22.5 equals 0.9 S. And if we divide 22.5 by 0.9 and we round, when we do some rounding, your calculator is going to give you a number, but because we have to have a whole number because we're talking about songs, you can't download like a fifth of a song and just pay for a fifth of a song, right? These have to be in whole numbers. So if we do some rounding, we find out that she purchased 25 songs. So she downloaded 25 songs. All right, that is it. If you have any questions, email me or use the help in ALEKS, but begin working on ALEKS. I'm going to divide. Actually, I'm going to give you a little extra ALEKS work, but it's still going to be 10 questions today. Tomorrow, you're going to do another 10 questions from the same lesson. So I'm giving you some extra work to make sure that you grasp this. And if you don't, send me an email and I'll see if I can help you some more. All right, have a great day.